Our presentation is about the binary use mineral admixtures for the advanced self-healing, autogenous self-healing in this strain hardening cementitious composites. I am Oğuzhan Öztürk from University of Konya Technical University from Turkey, and I also thank to my colleague, Dr. Marta Roig-Flores from Universitat Jaume from Spain. As we know, all our effort from different aspects, we are trying to design the resonance-driven structures. There are many different types of aspects in this concept. One is to make the concrete high ductile, damage-tolerant cement composites and by repairing their own cracks. Strain hardening cementitious composites is under the family of fiber reinforced concrete. Furthermore, by controlling the stress and energy criteria, you can get the very small bit of cracks in the excessive mechanical loading, under excessive mechanical loading. So then you can have chance to get to be self-healed under very severe damage. How to do it? We use some matrix modifications, as I will also detail further. But I just want to present this state of art. The problems of autogenous self-healing in the literature now is the self-healing in the wider crack widths, and another is the incomplete self-healing along crack path, and other is the stable self-healing products in the all again crack path. Here, this is another study that we made. This matrix is composed with carbon nanotubes and nanosilica, and you can see that here up to 1 millimeter crack you can get self-healing, autogenous self-healing. But you know, these comprises some complex matrix compositions, and therefore sometimes also this can be considered in terms of the cost efficiency. So instead of that, what can we do? What can we do is to synergistically use the mineral admixtures for the effective autogenous self-healing. First, we can understand the mechanism of the autogenous self-healing. There are some different aspects as RILEM proposed. First is the physical cause, that is maintained by the swelling of the cracks. Other is the chemical causes with continued hydration and calcium carbonate formation. And last is the mechanical causes. This comes from the impurity of the broken structure of the composites or from the water. As we know, the humidity and the water contact is very favoring for the autogenous self-healing. Why? Because in the water, carbon dioxide and carboxylic acid, which is very weak acid, this associates into carbonates, and these carbonates products react with the calcium leakage that are that come from the matrix, and then the calcium carbonate precipitate, and formation is done by the ongoing curing agents. So we should define what is the synergistic effect. The synergistic effect is lies in the fact that pore size refinement and grain size refinement. As you know, these are two different aspects in the composite. So we first single use methacholine and zeolite, then we use them with in the binary form. As you see, there are different types of aluminosilicate sources, and also they have different fineness in terms of physical properties. These are the details about the mixture proportioning. As you see, these are given by the mass. So if you can compare approximately the methacholine is replaced by 40% by weight of the total cement, and also the zeolite is same. And then for the binary use, half of both is used for the fourth mixture to completely compare the results. In the mixture, 2% of fibers, polyamide fibers, were used. As you know, this is important to get the strain hardening behavior. As you see from the mixtures, these are the mixtures have different types of blane fineness, so it is difficult to use constant amount of superplasticizers. Therefore, we aimed a flow rate. It's about 15 centimeter for each mixture, and we then defined the superplasticizer amount for each mixture. For the self-healing evaluation and for the mechanical evaluation, we used 3-point bending test. We used this 3-point bending test on purpose because we are trying to evaluate the potential of autogenous self-healing in the presence of binary use mineral admixtures. So, but when we use the sorptivity test, it is not favoring to use notch here, because we will also use it for the sorptivity test. Therefore, we make the stress concentration high by using 3-point bending, as you see from here. And even under, as you know, the 3-point bending, under 3-point bending, specimens undergo very abrupt and very catastrophic fail. But even under the 80% of the ultimate deflection, the specimens were able to resist the damage. As you can see, we get very high ductile behavior. After we obtained these specimens, we coated the two sides of the specimens with silicone, and then we used the sorptivity test for the evaluation of autogenous self-healing. Besides sorptivity test, we also characterized the micro cracks of specimens. These assessments comprises the crack width and crack number. As you see, first we defined the cracks, then you can also see the self-healing of cracks, multiple cracks. For sorptivity test, we used the sorptivity test at the first day, I mean, when the preloading was introduced, and after 7 days of first preloading, and then after 28 days of the preloading. The sorptivity test was evaluated in terms of the changes of mass during the capillary suction. We used the time intervals from 1 minute to 360 minutes, and we used the time root of these intervals to make to see the total behavior. Apart from the preloaded specimens, we separately evaluated the mechanical properties of the specimens. As you see, we used flexural strength tests and compressive strength tests according to relevant standards. To begin with, sound mechanical properties, you can see the compressive strength of specimens at 7 and 28 stages. As you see from the graphs, in the first 7 days, as expected, all mineral admixture bearing specimens had lower mechanical properties than the reference specimens, but at 28 days, the metakaolin was able to present higher compressive strength than the reference specimen. For the zeolite bearing specimens, both in single and binary form, we can see that the slow pace of pozzolanic reaction of zeolite, in this sense, the zeolite bearing specimens was lower than the reference specimens in terms of compressive strength. For the flexural strength, the similar trend is also valid for these tests. We can see that also in some literature studies, it is reported that the zeolite is even actively can react with the matrix up to 2 or 3 years. So considering the curing ages, this is really early ages. So we can see that the slow pace of pozzolanic reaction of zeolite. Here we can also compare the sound specimens in terms of the sorptivity test. As you can see from the lines, these lines belong to reference specimens. The use of all mineral admixtures significantly reduced the sorptivity index of specimens, because why? As I said in the beginning, first is the pore size refinement and the grain size refinement with the presence of mineral admixtures. However, among the mineral admixture, then we can see that metakaolin is the most reduced sorptivity index compared to other mineral admixtures. Also, presence of zeolite in both forms shows similar sorptivity index. This is for the preloaded specimens. As you can see, first, when the preloaded day, the specimens having mineral admixtures had the lowest sorptivity index. But once the curing age starts, as you can see from here, and you can also follow with the yellow, brown, and green lines, also with the zeolite, only zeolite bearing specimens, these specimens reduce the sorptivity index compared to other specimens, especially with the reference specimens, as you can see from the trend lines. To be more precise, you can also see the both comparison. For example, these gray is belong to sound, and the shattered gray chart belong to cracked specimens. As you can see, the first sound is lower than their preloaded counterparts, as expected. But you can see that the reference specimens showed no change during the further curing ages. But mineral-bearing admixtures showed lower sorptivity index compared to their preloaded specimens, especially beyond 7 days. You can see these two bar charts. And this was very pronounced for the metakaolin and zeolite-bearing specimens. As I said, we also assessed the crack widths and crack numbers. Here, we can see that zeolite-bearing specimens underwent a very high number of multiple microcracks. This was because of the rheology of zeolite, because in this strain hardening cementitious composites, we are trying to tailor the friction behavior of matrix and fiber by unirritated particles because of the zeolite. Then these zeolite materials probably made the matrix reduce the toughness, and therefore made the high ductile behavior, and accordingly we obtained higher number of cracks with smaller crack widths. We can also see the autogenous self-healed cracks. You can see that this, for example, this first belongs to this specimen. After 7 days and after 28 days, whole multiple microcracks of this mixture, binary use mineral mixture, close to their all cracks. This was also pronounced for the zeolite, only zeolite-bearing specimens, but we didn't observe so much progress in the metakaolin-bearing and reference specimens. You can see the specimen by specimen, the assessments of cracks. You can see that there are still inadequate self-healing products here for the reference. We just counted the totally self-healed cracks because we addressed the negative aspect of the autogenous self-healing. We just want to see the total self-healing. Also, it was also valid for the metakaolin-bearing specimens. And zeolite, we had almost, for example, here, we had almost total self-healing cracks. In the binary use of mineral admixtures, these specimens was very responsive to autogenous self-healing, as you can see from the specimens. For example, this image belongs to third specimen that have 4 different cracks. You can count the cracks and you can follow the self-healing process. Also, we made the same observation. If we are sure that we totally see the self-healing, 100% self-healing in the cracks. Now, in the future studies, we will also characterize them in terms of the self-healing products based on different mixtures, and also we will have some evaluation in terms of the mechanical recoveries like ductility, which is very important. To conclude, the compressive strength of all mixtures was able to exhibit more than 30 megapascal at 28 days. We can consider this value as applicable for the general purpose construction sites. Of course, the compressive strength varied between 7 and 28 days because you use the mineral admixtures. Zeolite bearing mixture showed the lowest compressive strength in comparison with the other mixtures, both at 7 and 28 days. Also, at the ultimate age, at the 28 days, compressive strength of metakaolin bearing specimens was only mixture that was found to be higher than the reference mixtures, and this result was also valid for the flexural strength. During preloading, mixtures with different mineral admixtures showed different cracking behavior, as I also presented the cracking results. Here, we can say that zeolite bearing specimens exhibited higher number of cracks compared to other specimens, and this was also more favoring for the self-healing behavior, autogenous self-healing behavior. As we obtained the sorptivity index, we see that sorptivity index in the both sound and cracked specimens at different healing ages shows that synergistically pozzolanic additions can improve the autogenous healing. Thank you for listening to me.